All right, these are the notes for 8.1. This is our third video. So this is part 3. In the first part, you were to find the first 6 terms in a sequence. In the second part, you learned how to write the rule for the sequence. Today, we're going to actually start talking about series as it compares to sequence and dealing with series. So the difference was sequence is just a list of numbers, okay? There's, so many numbers in the term, or it keeps going or whatever, but it is a list we use a comma in between. A series is actually a sequence, but it's added together. So you'll see a plus sign, or if you see a minus sign, that's because it's adding a negative. Okay. So a series is just a term of sequences or a sequence added together. So finite means there is a specific number of terms. So it ends. And then there's actually a sum. So you could add all of those up and you get a sum of 20. So if infinite series, you'll see it has dots and doesn't stop. Okay, so that means infinite goes on forever. When we write series, we use this symbol sigma to write in sigma notation or summation notation. You might see it written either way. We use that symbol to write these terms. And so for a finite series, like this example right here, and now it has it written in front. It really is actually written on top. That 4 should be above it, and it's I equals 1, and then the 2i is right here. It's just when I typed it in, that was hard to do. So I couldn't figure out how to get it done. So that's what it really looks like. That means you're starting with the nth term or k or I. Your book uses I a lot, so we'll use I, but this is really saying the same thing as n. So you start with the first term, so that's what that means on the bottom, and you stop at the 4th term. Okay, so that means I have a total of 4 terms. I start with term 1, which was here, 2, 3, 4 terms. And then this was the equation, like what we practiced in part 2, finding. Okay, so I added 2 each time. Whoops, plus 2 each time, plus 2. Okay, and 2 times 1 is 2. 2 times 2 is 4. So that was the equation. Now in a finite series, we can't actually get a sum. Like I said, this sum, because it has a beginning and an end, is actually 20. But in an infinite series, it has these dots. It keeps going forever. So on the top of our sigma is actually an infinity. Now we start at the first term. Now you have to pay attention on some of these where you're actually finding the sum. It might not start at the first term. So you start with whatever number's down here. You end with what is up there. And then this one was a 2i. Okay. But I can't actually find the sum of that without using some kind of equation, but we're not doing that in 8.1. So, but let's write the summation notation for a couple of these. So first we have to find our rule for the nth term. Okay, well I look at this and I know I add 6. Now this is from yesterday. This is from part 2 where we worked on finding our nth or our equation for the nth term. So I'm adding 6 each time. So if I'm writing that rule, I know I'm going to multiply n by 6. Okay, so if I start with the first term, remember this is term 1, 2, 3, 4, 5. You might want to draw the t-chart if you need to. But if I do that and I plug in 1, I have 6 times 1 is 6. But I actually wanted 5. So I'd have to subtract 1. Because this is the first difference, which means it's the difference of my actual sequence, or in this case, series. It means it's linear. So I do know it's going to be the 6 times n, and I just have to figure out what I'm adding or subtracting after that. Well, right now it's looking like it's going to be 1. Let's try that second term. And that's 12. But I actually want it to be 11, so yeah, I do have to, oops, so that would have been a 5, and that is now 11. And then if I keep going, the third term, well, that's 18, but I wanted 17, and it keeps going. And you double check all your terms, make sure you're on the right track. So that's 24, but I wanted 23, so I had to subtract 1. Oops, that's a 23. And then that fifth term, 6 times 5 is 30, but I actually just wanted 29, so I had to take 1 away. So to find my nth term here, it was 6n, and then I had to subtract 1 from it, okay? So that's the rule, but it wants us to write this in summation notation or sigma notation. So I'm going to draw my sigma. I'm starting with term 1. So on the bottom, I'm going to use the variable I. You could use n, you could use k. That part doesn't matter, but whatever you use right there is what you're going to use in your equation when you write it here. Okay, so my rule, so if you used n, that's fine. Just leave n, and then this is n on n, and we're starting with term 1. But we have 5 total terms, so I'm putting a 5 on top. And then this is how to write this in summation notation. Now, I'm using I specifically because your book uses it a lot. So that's what you'll see in Big Ideas. But you can use any variable as long as you understand when they have it written with other variables, it's the same thing. That's just a letter. You can think of it as x. X equals 1. And then I have 6x minus 1. Those are all the same. So if we scroll over here to number 2, let's try to figure out what's happening here in our sequence so we can find our equation for an. Well, these are fractions, but everything, I'm not adding 1 each time. In the numerator, I'm adding 1. That's true. In the denominator, I add 1. But that's our n is 1, 2, 3, 4. But our an is 1/4, which is like 0.25. And then 2/5, which is 0.4. And 3/6, which is 1/2. So those all change, and the pattern is a little trickier to see. But what I can see is on the top of each of my fraction, I have its place number, okay? I have my n. My n value is 1 in this first term. It's 2 in this second term, okay? So I know on the top for my rule, I'm going to have n. And then on the bottom, well, it's adding 1 each time, so I know the bottom is linear. So if I'm just using these as my terms to find the denominator, well, it's adding 1, so it's 1n. Well, we're just going to, 1n is the same thing as saying n, except in this first term, this is n is 1, but I want 4, so I need to add 3 to it. All right, let's try and see if that works. So if I find my first term, so n is 1, I end up with 1/4. Okay, so that worked out. Now let's try it when n is 2. I get 2/5. All right, so far 3, and I end up with 3 plus 3 on the bottom. So I have 3/6, which is 1/2, and then I do when n is 4. Whoops. So I end up with 4/7. So that is my rule, but to write it in summation notation, start with your sigma. We're starting with the first term here, so I or k or whatever one you choose to write with. And this has dots on the end, so it goes to infinity. And then I write my equation there, but I'm going to use the variable I because that's the variable I put in my sigma. All right, so for number 3 here, our series is a little different. It looks like if I'm going up, like this one is the 4, from going 3 to 4, it's adding 1, but it changes sign. That's the pattern I see each time. It adds 1, but then it changes the sign. If it's positive, it changes to negative. If it's negative, it changes to positive. And so this is going to actually be a combination of 2 of our functions here. So let's see. So this is like term 1, 2, 3, 4, 5. So I'm just going to start my sigma notation here. And really, sigma notations have these little things there. I don't generally draw those just because I'm not the best drawer, but there we go. I said we're going to start with I. We start with term 1. We're going to end with term 5. I at least can get that far of my sigma notation without even writing the rule yet. But now let's find our rule. So when we change signs, like if I say change the sign of both sides of an equation, like you have negative x equals 2, well, you either divide by -1 or you multiply by -1. That rule is the same. So I'm going to say, okay, let's try, if I take -1 and I take it to a power. So that way, if it's to the first power, it's going to be negative, which my first term is. If it's to the second power, anything squared is positive, so it becomes positive. -1 to the third power is negative. -1 to the fourth power is even, or I'm sorry, is positive. So it goes along our series there, but now we need to actually get the correct number. So that took care of the negatives, okay? That's how you'll take care of these. Now that's when it starts with a negative. If it started with the positive, I'd actually add a 1 up there with the n, but I don't need to do that for this problem. Oops, and I wrote the letter N. Oops, I'm getting all messy here. What's going on? But actually we're using the variable I. I guess I should need to be consistent. And then let's see. The change, it's going up 1. That took care of the pluses. But to get from 3 to 4, I add 1. 4 to 5, I'm adding 1. 6 to 7, I'm adding 1. So that change is consistent. So I know it's going to be linear. So I'm going to have this times I times 1, which is just I. Now, if I'm trying to see how that works, let me come over here and say, okay, to get my first term, if I have -1 to the first power times 1. Well, that's just going to be -1. So that wasn't quite enough. I actually want it to be -3. So let's do 1 plus 2. That gives me that number of 3. And that -1 to the first power out there gives me -3. Okay, so let's try that. So let's try -1 now squared. And then I have 2 plus 2. Well, that's a positive 1 times positive 4 would be 4. -1 to the third power is -1. And then I have 3 plus 2 is 5. I wrote 5 instead of parentheses. So -1 cubed is negative times 5 is -5. Okay, so I do see that that pattern is holding true, but what I needed to add in there was this plus 2 business. So in my equation, I have to have plus 2. Okay, so there's the sigma notation for number 3. All right, so let's move over to number 4. And this one I can easily tell I'm not just adding some simple number each time. I'm not just 6 plus 30 is 36, but 36 plus 6 is not going to be 216. But I do kind of see a pattern quickly with multiplying. What if I were to multiply by 6 here? 6 times 6 is 36. Well, 36 times 6 is 216. And 216 times 6 is 1,296. So there's my pattern. This is not linear. It is not quadratic because I am multiplying. Well, we talked about this in part 2. So if I draw my sigma here, okay, we're going to start with we start with term 1. Now this has dots on the end, so it's going to infinity. Now this is saying I'm multiplying by 6, so I'm going to take 6 to a power. And that's what's changing each time is that power. So for my first term, which is right here, oops, let's do a different color here. Okay, when I is 1, so 6 to the first power is 6, so that works out. When I is 2, that 6 squared is 36. When I is 3, 6 cubed is 216. And when I is 4, 6 to the fourth power is 1,296. So this actually is my sigma notation for number 4. All right, let's move on to number 5. Now, this time it's actually wanting me to find the sum. So it has it in sigma notation. So I start with sigma notation and I'm going to go from there. So I find it easiest. Let's draw our little chart. This tells me I'm starting with term 1. This tells me I'm ending with term 5. So I'm going to count all the way up to when n is 5. Oops, need to go a little farther. Okay. So I'm going to plug a 1 in for I. Okay. So this is 8 times 1 is 8. 8 times 2 is 16. Now, these are added together because it says sum, which means that should tell you right there, addition, but this is a series, and that's what's between the numbers in a series is an addition sign. And then we have 8 times 3, which is 24. 8 times 4 is 32. And 8 times 5 is 40. And you just plug all that in your calculator or in your head, whichever, and I get that the sum is 120. All right, let's move over to number 2 here, under finding the sum. All right, if you notice, the bottom of this sigma notation is not 1, it is 3. So when I'm writing my terms out, instead of starting at 1, I'm going to start at 3. And that top number is a 7, so I'm going to count until I get to 7. All right. Now, I'm going to plug 3 in for k, and I get 3 squared minus 1. 3 squared is 9, minus 1 is 8. Okay, 4 squared is 16, minus 1 is 15. 5 squared is 25, minus 1 is 24. 6 squared is 36. Subtract the 1 is 35. And then 7 squared is 49. Subtract 1 is 48. Okay, so you can write it. Sorry, I'm going to zoom out here real quick if it lets me. You can write it in your table if you do the table, how it goes, and then write it out like this. Or in this problem, I kind of jumped. I just plugged things in and then got my terms. And now I know I need to add each of these together to get my sum. So I just plug all that in my calculator. And if I did it right, you should get 130. I believe that's what I got. Hopefully that works out for you. And so that is my sum of that sigma notation right there. And if I come down to number 3, this one looks a little different. And it goes all the way from the first term to the 34th term. So yeah, I could go ahead and write my table, but starting at first term, and it's going to keep going all the way to term 34. Okay. And this just tells me there's no variable in it. So each time it's 1, and it's adding 1 each time. And I know I have 34 numbers that are all number 1, and they're all being added together. So I know my sum is actually 34, because 1 plus 1 plus 1, 34 times is going to equal 34. So that one just looks a little different because there's no variable. So I can take the 34 times that 1. So if that number would have been a 2, I could have taken 34 times 2. And then number 4 here. Let's do my little chart. This starts at term 2. This should have said k equals 2 on the bottom. I'm sorry, I had a typo. And it goes all the way to term 8. And I said 8 and wrote it. 4, 5, 6, 7, and 8. And this is 2 divided by k. Well, in this first term, and I'm writing an, and I realize I'm sorry, I should have written, this is k and this is ak. Okay. All right, so 2 divided by k, and my k is 2, so 2 divided by 2 is 1. 2 divided by 3 is just 2/3, just leave it alone. 4 is 2 over 4, which does simplify, and I like simplifying, which becomes 1/2. 5 would be 2 over 5. 6 would be 2 over 6, which simplifies to 1/3. Then we have 2 over 7. Then we have 2 over 8, and that simplifies to 1/4. And we know we're adding all these terms on the bottom because this is a series. So if it just wanted you to list the series, that's what you would list with the plus sign in between them. Okay? But we're actually finding the sum. So I plug that in my calculator, and it gives me a decimal like 3.66, but it goes on, or it's a lot. But your calculator can change it to a fraction, so it's exact. Since all of these numbers are exact, you should get an exact answer. And it becomes 481 over 140. And that is the sum of number 4. So you have learned all the parts of 8.1. Watch the videos in order, take notes, and now you're ready for your 8.1 quiz.